Another lesson before lunch, I think. We can have this one. We can start at least. As I told you, inside the rocks we have many different types of minerals. So minerals is the building stones of a rock. If the house is the rock, then we have some building equipment that is the minerals, and they are going to be nailed to each other in different way, and it depends on how they behave, how they look, and so on. So in mineralogy we have to consider crystallography, and to see how, you know about atomics, and you know all about crystallography, so I will not tell you anything about it. But if we have in crystallography, you know, they can be some cubic ones, cubic crystals, and they can be face-centered cubic crystals, they can be inner-centered cubic crystals, body-centered, yes, and so on. And this is very important for how strongly the bounds will be between the old mineral, the different types of minerals. And if you are looking at this one, this is a calcite, calcium carbonate, and we know that this is not a cubic system, because you know that the angels, this is surface, mineral surfaces, and they are not 90 degrees at any kind. But if you had a cubic one, there should be 90 degrees edges everywhere and lines everywhere. So that's why we are looking at this one, and it's a way for us to determine what type of mineral this is. So we know that this is calcite, but we also know that they have a special chemistry. So if the outlook, it looks like a special way, but we also know that it is a special way of these components inside this one. This is a calcium, and this is carbonate. So calcium carbonate will stick together. And if we have this one, this is very similar to look at. They are white and they are lustrous, so you can see it, but they are quite different in their chemistry and their crystallography. So, and this is the chemistry of this one. This is quartz. Many of you have watches, which you have some quartz inside your watches, and it is just like this. You have there is a smaller one probably, but if you have a big watch, you have to have a big crystal. And this the content here is silica and oxygen. Silica and oxygen combined, that is what we call a quartz. But it can look very different. It's not only these crystals we can see here. It can be like a glass, just looking at this one, but this can also be a very dull white stone, which you are finding outside the parking places. We call this a milk quartz, because you cannot look into it. This one is very, very nice. It's bright and looking into it. But it can also be like this one. If you go just to look at the chemistry, this is a flint stone. But this is not yet, or this is not originally a stone, but this is a microbes. Silica algae, which have have died and fallen down to the bottom of the sea and come together, and they are in the silica, and they were just like SiO2 as a silica oxide. So, but this is not any crystals in here. You cannot find it. If you are looking at this one in a microscope, you will not see anything. It's just grayish nothing. But if you look at a quartz inside this one, you can feel different refraction colors. Very nice. So if you are trying to look at minerals, you have to watch them with your eyes. You have to knock on them. You have to smell them. You have to see how hard they are and everything like this. So this is what we call a physical properties. And you know, geology is not a very high technology equipment when we are out in the field. We are using this one, a knife. It's not high technology, but it's very important to have this one, because if we are looking at different types of minerals, where I can make a mark in this one, and then I know that this stone is not as hard as steel. But if I take this white one and I try to make a mark in this one, there will be nothing, because this stone is harder than the steel. And that's good, good knowledge to know. And then we have this magnet. Yes, it's not so high technology either, but there are some special minerals which we can use to have this one, these black ones. If we put at this one and there is nothing, you can be completely dead. But if we take out our magnetite, we can feel that this is very, it is working like this. And also there are some other minerals which is magnetic, which we can find with this one. And then we also bring some fuses. This is just a 16 ampere used one. And what are we doing this one? That is when we are looking at different minerals, we can see if I have one special mineral here. If we are looking at sulfides or different type of oxides, they can be very difficult to see whether they are copper sulfide, if they are iron sulfide, if they are nickel sulfides, and so on. But if we are using this one, we can try to make some we can make some mark on this one, because this is not, what do we call it? It's not glaciated area, it's just pure porcelain. And if you are using this one, we can find and separate different minerals from each other. So high tech, no. But it's very important knowledge, yes. To know about all these minerals which we are knowing, and particularly rock forming minerals. We are also having, I said, smell. I have a special mineral here which is calcite, and sometimes we have this calcite containing a lot of organic material, and if we are doing like this, you're gonna smell them.
Yeah, it smells like fun.
Yeah. No, it smells. It's civilization.
Oh yeah.
Yeah, we can send them around, and they are smelling petrol. So this contains about 30% oil. So if I'm heating them up, we can extract some petrol from these stones. You cannot put them into your car directly, but almost. We're going to see them, and you will collect some on Öland on Saturday. Probably, I hope. So you can smell them, you can see them, you can feel them, you can do everything with them, these minerals. And that's why we are having special types of crystallography, chemistry, and silicates. That is what we call these rock-forming minerals. Almost every rock-forming minerals, they are containing silica. But in a sense, there are some rocks which will not contain silica. For instance, limestone. Limestone contains calcium carbonate. But in other way, different hard rocks like granite, gneiss, porphyry, gabbro, and everything, they contain silicate. Here. I will not tell you about it because this is what you know much better than I do, because I'm a geologist. We have these 7 different systems. We have a cubic system, we have hexagonal system, we have rhomboedral system, tetragonal, orthorhombic, monoclinic, and triclinic. And you know all this very, very, because this is the, it depends on how the space jitter is located. The elements are placed in this space jitter. So I think that you know more about this than I do. So rhomboedral system, that was the calcium carbonate. This is a typical rhomboedral system. And then we can see, if we are going to look at this one, in a cubic system, we have all angles 90 degrees, all borders, surfaces are the same. In other way, it will not be cubic. So 90 degrees and all surfaces at the same size. If we have the hexagonal system, we have a pillar of 6 sides. Rhomboedral system is that one, the calcite. Tetragonal is have you ever been drinking some milk? Have you been drinking? Yes. We have a company in Sweden which is called Tetra Pak, and they are creating boxes for milk and for liquor, not alcoholic, no, but other, and they are, you know what it is? Tetra, yeah, Tetra Pak. It's not like this one, no. It could have been. It could have been. Orthorhombic system. You know what orthorhombic is? This one. You know, it's elongated, but it is 90 degrees angles, but the sides are not the same. That's orthorhombic. And then we have monoclinic system. It's almost like this one. If we had made this surface a bit not 90 degrees, we have had monoclinic. And if we had a triclinic, there is no angles 90 degrees, no surface at the same size. I used to say that if you are driving over this one with a car on this side, there will be a monoclinic one. And if there come another car driving over on this side, we have a triclinic car. No, triclinic, mostly this one. Oh, you know about this one. I will not tell you more about it. The 8 most common elements in the crust forms the most common minerals, such as feldspaths, quartz, micas, pyroxene, olivine, amphibole, olivine, and calcite. You know, these 8 most common elements was in the last picture I had on the crust of the Earth. It was oxygen, it was alumina, it was silica, it was magnesium, it was sodium, it was potassium, and iron. Iron Maiden. This is not here. Iron Maiden is in as another mineral. If we are comparing silica and oxygen, like this one, in a tetraeder system, we have silica in the middle, and we have these 4 big oxygen ions around it. And in this small silica in the middle, then we have this tetrahedron, and we have silica tetrahedrons. And this is very important because these silica tetrahedrons is going to build up the minerals which will contain these granites, will contain to go up to every hard rocks we have and where we can put down our waste into this. So this is very important, and they are called silicates. At the at a famous university in Gothenburg. No, I know that I was educated in Chalmers University of Technology, and we have this Royal Institute of Technology in Stockholm, and in Gothenburg we have this other one. This is the two most famous technology universities in Sweden. I was educated in Gothenburg, and Vaclav is in Stockholm, but we can combine all the way. So, but there is an institute which is called the Silica Institute. They are doing research only on silicates, their behavior and how they can use it, and so on. So, if we have for instance silicate. Most geologists saying silica, okay, that is quartz, this white, dull mineral. But if we put this one dull mineral into your watch, and you also have a small battery here, and you put some energy into this mineral, it will start to fluctuate like this one. And this is what we call a piezoelectric area. But we can also use silica and press it, and we create some small energy electricity from this one. So it is very important to see how we can use this one to collect solar energy, to collect everything that we can use this one for. And it is a very important thing. It can be very dangerous if you have too much silica when you are making concrete, because then we can have some problem with the concrete, because it will not be as hard as it could be, because silica is always combined together with if it's not crystalline, we can have some new silicate inside this. If you press this very hard, small silica will dissolve and create new uncrystallized silica inside, and it is like this one. This is uncrystallized silica, and if you put this one into concrete, you will have big problems with the concrete. It will fall apart. And so was the problem when on this bridge which you are going to pass over when you are going to Öland. We have had big problems with the concrete in these pillars holding up the bridge. But it's no problem. On Saturday, it's no problem. We hope. It will fall apart. This bridge was constructed in 1972, and every year since then they have been doing some repairing works on this one because of different types of what happened. So silica will bind 4 oxygens and form this tetrahedron, and this is very, very important for everything which contains minerals. And there we have 6 different types. of silicates, nesosilicates, and nesos is Greece, if from Greek, and you know what nesos means? Island, Polynesian. Nesos, which means this is an island. So it is only separated tetrahedrons combined together with another tetrahedron with another cation. For instance, potassium or sodium or magnesium. But the silicate tetrahedron is separated from each other by other cations, by other metal cations. So that is very important. Sorosilicates, this means a pair, a couple, so that two silicate tetrahedrons is combined. So these two silicate tetrahedrons are sharing one oxygen. And that's good. This is different minerals, olivine, and this is epidot, and they are green, nice minerals, but I will not give you this one. Cyclosilicates. Cyclo means a ring, cycle. This is a cyclosilicate, and this is mostly minerals which is, I'm sorry, I don't have any cyclominerals. They are mostly formed like pillars, long as one mineral. Inosilicates, that means chain, and we have double chains and we have single chains in this minerals. And this is a very important for creating this black basalt, which I told you was the main bedrock on the ocean bottom. This is this olivine. They are black. This is a pyroxene. This is just black. It's just a black stone. You might see it. And we also have a amphibole. This is also a black stone. Sorry, you cannot see it down there, but you can go here and I will tell you everything about these amphiboles and this pyroxene. I will show you. This is, and then we have some phyllo, which means leaf, a leaf, and phylosilicates is like this. You cannot see that, probably don't recognize that this is a type of stone, but it's what we call muscovite, stone from Moscow. And this is what we call a phylosilicate, and it's micas. You probably have heard of micas before. You can have them white, and we can find them a bit darker. It's like fish shells. And they are always in different type of rocks. And they are very special because if we are heating them up, they can behave very, very, very strange. Some of them will swallow. If they put some water into them, they can swallow and crack hard rocks like this one, so that there will be new fissures inside this one. It had been very big problems if you have these fissures, if you are creating tunnels for roads, for cars, and for trains, and so on. And if you put down, if there comes some water inside, they can fall down stones on the head of the drivers or the passengers also, if you are unlucky. Textosilicates, that is what we call a quartz. That is every edge of this tetrahedron is combined to another silica tetrahedron. And all these other elements which we have inside, they are combined to other forces, not combined with these edges to each other. Are you tired? We have some physical properties. Cleavage. So if I smash a stone, with my hammer, I didn't brought my hammer. This is also high technology hammers, which is just an ordinary hammer. But if we smash a stone, some of the stones will fall apart in very fine sides. This would got a big cleavage system. And if I smash another stone like quartz, there will be no cleavage system at all. You cannot see any of this cleavage system. The best cleavage system is one of these micas, which is perfectly cleavage system. So that is the cleavage system. This is also for calcite. You can smash this one and you have these surfaces. You can always see them and you can measure the angles, and then it's no problem for us to understand what they are. Pyroxene, also good cleavage system. Flint, no cleavage system because there is no crystals. Cannot be any cleavage system in this one. This is like concrete, it's not crystallized. So that is the cleavage system. Surface structure. You can see on the surface if it is I said color and luster, but the surface system, if it's smooth, or if it is a rough one, or if it's glittering, or if it's different types of lustrous, is the surface structure. You cannot. If you look at this one in a microscope, you can see that there are some small holes and small hills on the surface. You can see them very carefully. Hardness is no problem. If you have this nice knife with you, you can, of course, try. You see this one? This is talc. This is powder. This is just if you are lifting heavy things, you sometimes use this on your hands. This is, or if you have a baby, you will have this baby powder. This is just stones which you are milling down like this. You can see. Very good. Feel it. There's no problem. No. It's very good. And you also use it industrial when you are making backlav, när man gjuter, vad heter det? Gjuter.
To cast.
Gjuta ihop, ja.
Yes.
To cut different parts for metal parts. Yeah.
Casting.
Cutting. Inside when you are doing this forms, inside the forms when you are doing this one, you use this talc. And have you vad heter kamin? Sådana täljstenskaminer. Kamin, eldstad.
Ingen aning.
When you have some fire stoves, you know, and you are when you are going to heat them up, and you can use this rocks forming minerals to make these stones, because they are keeping the heat very long. So use them in this one.
Very good for sauna and bastu.
Yes, a sauna and bastu. Yes. Yeah. So this is very important. They are not so familiar. But we call this one, if we have hardness, you know, geologists, they say that there's a gradation of 10. So this is number 1. This is the softest mineral on Earth. And the hardest mineral on Earth is diamond.
Well, you should show some diamonds to the ladies. They are very much.
Yes, but they, I used to have one, yes. But last course, it disappeared. It was a huge one.
Going on.
Yes, yes, I borrowed it from a lady. Then we have the density. The density, yes, you can feel this one. It is very heavy, and you can also have this one. Which one is heaviest?
This one.
This one, yes. Now they are not as big as each other, but you can feel this heavy. In other way, you know, when we are separating iron ore from the rock-forming minerals around the rocks, we are using there is a magnetite, and we have also hematite. Hematite is another type of iron oxide, but it is not magnetic. But this one is magnetic. But if we have an hematite, we have to separate the iron ore from the rock by density. And then we have some, you know, we are milling down the minerals and the rock together, the iron ore together with the rocks, and then we are milling it so small, and then we put it into the water, water sludge, and we are putting this water sludge in a spiral, and the water is going very fast, and the heavy minerals, they are very close to the center of this spiral, and the easy minerals, they are going outside, and there are some small holes in the spiral inside, very close to the center line. So we are taking out the heaviest minerals from these light minerals outside there. So it's very high technology. It's just making a sludge of everything, and we are separating it by density.
Also the principle of the isotope separation based on the masses.
Yes.
The centrifuges.
Yeah, the centrifuge, yeah, yes. It's like a centrifuge. But if we have this one, this is the magnetite, we crush it together, and then we use very strong magnets. And we have this crushed material, and they are going on a combiner. You know what that is? Combiner, yeah.
Conveyor belt?
Vad heter det? Det är sådana här transportör.
Conveyor belt?
Transporting, yeah. Transport the material at a very high speed, and then when they come down on the edge, there is a mineral magnetite, so that we can separate the magnetite from the rock by this magnet. And we have two separate piles, one for the iron ore and one for just the stone. Very simply. But that is very good. And color, yes. We are white. We have almost something like this. I don't know, Turkish. No, turquoise. I don't know what it's called in English, but it is some greenish. And then we have some reddish. And we have some white. And we have some black. And you can have almost every, here is a green one too. This is very nice. A green one. So this is, the color is very special, but it is not the same color when you are looking at them in a microscope. So when we are a bit curious about what is this for type of mineral, we cut a slice of this one. We cut it into 0.25 microns, and we glue it on a piece of glass, and we also glue another piece of glass on the top of it, and then we have a polarized light coming into this preparated mineral, and we can look at it, and then we have different color for every type of mineral we have. This is the optical determination of different minerals. And there's some tables about this one where you can go into to a book or something where you can find this, and you can always see what it is. But there, the feldspar, this one is a feldspar, potassium feldspar. You can see that is mostly reddish. But if you look at this one in the microscope, it is only black and white, but it has a special special feature. It looks like, you know, a cloth which is in the kitchen. There's some lines going across each other, and that's how this one looks like when you're looking at it in a microscope. So it's very important to have this microscope to look at this, to different color, rub color. This is when we are using these ones, especially for metal minerals. So this is iron sulfide, pyrite, we call this one. And if I grid it here somewhere, you see there's nothing there, and I grid it, it's almost a greenish black color of this one, but it is normally very yellowish, metal yellowish, but it's a greenish black color on this one. And then we have some, if you have some mercury, it will be pale red on this one, but mercury in this one is only metallic. You can see that it's almost like iron metal, but if it's mercury in it, we can see that it's a reddish one. So that is what we are using, this one. Luster. Some minerals are dull. There's no luster which we can see. They are just like magnetite. It's black. And then we have this. This is a good luster on this one, quartz. You can see, you can feel it. You can see this very illustrated. That is very good. Magnetic, we have talking radiation. If we are looking for uranium, we can trace it by the radiation, of course. Uranium oxide is not so common, but you can find it, and normally you find uranium in what you call it, granitic rocks. It never in basalt and lavas like this ones, but in granitic rocks, what we call it higher content of silica, higher content of just silica, not the quartz, but the silica, high content of silica. There is a good affiliation for uranium to be there, and this is a typical mineral piece of rock where we should be able to find uranium in this one. This is what we call micas. We have feldspars and we have quartz, and this is 3 typical minerals for a granite rock. And so we call it salic. That is what we call not a base. Basalt is is not so sur.
Acidic.
Acidic, yes. Not acidic. The uranium is very common in acidic rocks, but never in this basalt or diabase and mafic rocks. Fluorescent. it's very, very uncommon. But there are some minerals if we are using ultraviolet light and you are putting the ultraviolet light into some minerals, you can have another type of color. Very typical. I was working as a young student. We were looking for scheelite. This is a sort of wolfram calcite mineral, and it is fluorescent. So we have to work during the nights, and it was not so. It was up in the north of Sweden, and you know. We don't have any nights up there. You know, the sun is almost shining all day, all night, through the whole summer. So we had some problem with this fluorescent looking at this mineral, because it was broad light even at 12 o'clock in the night. But so we didn't find any scheelite. But we were working there 3 months. It was not so interesting, but we were walking around in the forest, and I also want to show you that there is sometimes we have some minerals which have a very special feature. This is what we call. No, I haven't really, but special. This is what we call it asbestos. This is a mineral too, and it's not so. That's no, there's not so good. But this, well, it's forbidden nowadays in Europe, I think, to use it. We had it in our breakings, and also in tubes for isolating and tubes for ventilation.
Yes.
We had this asbestos, and they are very, very poisonous. So they will not grow older and older. So they stay like this, because if the algae is coming here, they will die, and if anything else will come there, it will die. And if we are working with it, we will die. So, so this is not so good, but it has very good properties. You know what? One thing, there was someone who had been drinking. Yeah, I asked you if you have been drinking. In the past, when in Sweden we are not producing wine by ourselves, but we are imported wines in big tankers, and they came to Stockholm, and to filtrate the wine we used asbestos. I never drink wine.
No, but I mean, but Tommy, one must refer to it. Actually, the danger with asbestos is cancerogenic feature when they are actually in the air. They are very, very fragile, so they are breaking into small needles,
yes,
getting into your
lungs,
yes, and then staying there, actually irritating the lungs until they generate actually the cancer behavior.
Yes, and those who are working with this one, because they were milled it down, very, very fine-grained material, and then pressed it together into plates to have them on surfaces for houses and so on. But those workers, there are no one left of them. They have died, everybody.
And the very good feature of asbestos was also why it was so popular. It was very tolerant to high temperature.
Yes.
Good isolation and not distracted by the high temperature.
Yeah.
So in the metallurgy industry,
yeah. I once visited a mine, asbestos mine on Cyprus, island Cyprus down there, and the real problem they had, because they crushed the ore into fine particles, and you couldn't take a photo because it was glittering in the air of these small needles of asbestos. And the problem there was to find workers, because they had to find them very long, far away from the mine, because people are dying very close to the mine, but they couldn't figure out what was the problem. But Now we know what the problem was. So no, we put it down here. No, we don't have to use that one. Oh,
You don't have PESH blend, the uranium ore, you don't have here uranium ore.
Uranium ore? No, it's out in the car. No, I don't have it. PESH blender is one of these minerals. I once found it in Gothenburg. There is a pegmatite where they were excavating some feldspars. You know, feldspars they're using for this making porcelain. Feldspar porcelain to plates and to cups and so on. And there in this rock, we could find some small PESH blender minerals, because you can see the radiation going into the feldspars. It was a burned feldspar spots. It was not so much, but very, very little. But we can find, and we were very, very excited, of course, to find this.
Once you mention asbestos, people from Poland, they should know the origin of the name PESH blender, because actually PESH is either pech in German and the Czech is actually in Polish, which is bad luck.
Okay.
Because people were dying actually in the uranium ore also because of the inhaled cancer. So this mineral was called the bad luck ore. So PESH blender in German is actually bad luck. Bad luck ore. Oh. So that's the same origin. That's the same reason why asbestos. But they never call it PESH blender.
No.
Uranium ore was called the bad luck.
Okay. Yes, but during the 1970s in Sweden, we were prospecting for uranium a lot. A lot of students during the 1970s were out looking for ore, uranium ore, and there are some, you know, sometimes we can find some in a black slate like this one. Black slate, there is always some uranium. If you can measure the high radiation, you can make a utslag. You can see it in the instruments that there is some uranium in these ones. It's not so much, but we have in special places in Sweden we have some minerals, mineralizations of uranium. On Öland, where we are going on Saturday, they were looking at this one because there are some black slates, but it's so very thin. It's not the way we are going to see it. It's not more than 1 meter thick. But in the south of Öland there can be about 17 meters. But they were interested in trying to see if they could excavate some uranium from this one. But I will take that when we talk about the sedimentary rocks. I think you will have some dinner or lunch. Mm-hmm. Will you have some lunch?
Yeah, of course.
Yes.
So
okay, yes, that will be good for
Convey meeting here at 1:30. No delay, no sleeping after the lunch. Okay, so we are reconvening.
Okay. Okay.
Sit down, guys.
Okay, we will continue with these rock-forming minerals. As I told you, we had special rock-forming minerals which is almost in all these rock types, which we can determine or decide. We can detect in the ground, and we had feldspars, we had quartz, we had micas, we had amphibole, pyroxene, and olivine, and we also have calcite. So we will talk more about these minerals just to see what they are, how you can find them, and what their properties are. So feldspars, as you can see, it's a potassium feldspar. They have potassium, alumina, silica, and oxygen. And also here sodium, alumina, silica, and oxygen, and calcium, alumina, silica, and oxygen. So these metals, potassium, sodium, and calcium, will turn up into different types of feldspars. But we call them the family of feldspars, and 58% by volume of the Earth's crust is feldspars. So you have more than 50% chance to find, if you pick up a stone, you find feldspars in it. Anywhere you go during on the whole Earth crust. They are very common. And the most common one, okay, I will show you the pictures of it later on. This could be straight lines in this triangle, but I'm not so good at drawing in my computer. So there was some. But I have probably been drinking a lot during the last month, so can be so. But what is you can see this triangle. This triangle is very common in geological descriptions. And here we have potassium, sodium, and calcium. And this area, which I have marked up here, this is the one. You know how to read this diagram. Up there we have 100% potassium, 0% potassium down here. There we have sodium. So we have lines like this, and every line makes up, every cross is 100% of everything. It's together with that. So in this area, when we find a mineral in this area, we call it potassium feldspar. And when we are in this area, has another, I haven't written it, but it's called plagioclase. But it is two different types of feldspars. In this area, you can never find any feldspars. But it's impossible for them to have this composition. So we have potassium feldspars, and we have this alkali feldspar down here, and we have calcium feldspar in this area here. And potassium feldspar is very common in acid rocks like granite and granodiorite and so on that we have up there. It's more in this area. In sodium here we have diorite. We have, if we go over to this area, we have something which is called gabbro, and I will show you these names later on. So it is very, very important to know about these feldspars, and we can find them in most every type of bedrock, even mafic, black ones, or acid, and also intermediate. So they are very common. We don't find them in limestone, because limestone is sediments from this calcium carbonate. Just calcium carbonate, or marble is also calcium carbonate. So, but this is almost the only one, and also in organic, like coal, charcoal, and so on. There would be no feldspars. Anthracite, this is only carbon. But feldspars is very common. Another very common mineral is quartz. 11% of the Earth's crust is there. It is, you cannot find it in this mafic black rock types. There's no quartz. It can be there as a silicate, but not as free silica. It can be there together with calcium and alumina and silica, but it can never be there as SiO2 in this form. This is only we can find it in acid rocks like this one, quartz. You can find it here, and it's quartz. You can see it in many different types of color: white, pink, brown, yellow, and purple. Anything you can almost be any type of. It depends on just SiO2 is like this one. It's bright and it's white and it's you can see into the crystals. It's clear. But if you put some other, you know, a polluted quartz, then we can have some purple, and we can have some yellow, and we have some brown and pink and so on. But those are very famous. Amethyst is a purple one, which is used as a game stone, which you can necklace and you can have it in rings and so on, because the purple color is so nice to see. And the pink one is also very. I don't have it here. But all these special ones have very often disappear from my collection because they are so nice to look at. So it's when I send them around, everybody have to look at them, and someone forgets to give them back to me. Yes, and diamonds and so on also. Yes, but. That's why I don't have any more. I have to go out for watching to find new ones of this type of minerals. We have feldspars, we have quartz, and we have micas. These three types of minerals are the main minerals in granite rocks. And micas can be of white and black ones. There are 8 different types of micas, but the one most common one is a black mica. I will show you around this one later on. And this is the white mica. And together with you see that this is also potassium, alumina, silica, but also an hydroxide group at the bottom. So there must be some water in this crystallization system. Let me say so. There's originally in a magma deep down in the earth, we have about 4% of water in this magma. But as the crystallization goes on, the temperature is falling. Minerals are elements are coming together to create minerals not containing water, not containing so that the water content will rise in this magma. So at this end stage, we have about 14% of water in this magma, and that's why they can be so violent when the eruption appear, when they come up there, because then water can create this very high pressure. And if we have this high water content, at this stage, this mica will be created. And also, as you will see in amphibole, this is also a hydroxide group in this mica, this mineral. So they are at the end stage of the crystallization time for a magma. When it's cooling down, we have the rise of water content in the magma. And that is very very important. Muscovite and biotite. most common in Salic, that is acidic rock types, and also like granite or diorite we have there. And I made some pictures of these minerals because it's difficult if I send them around and I'm talking about one mineral and you are looking at the mineral 10 minutes ago. So that it's not so easy. But this is the feldspars, and as I have shown you, and this is the green one, and we have this white one, and we also have these red ones. This is different types of feldspars. This is what we call potassium feldspar. You know, up in the left corner. This is at the bottom of this feldspar triangle with sodium and calcium. This is this mineral. Of course, they have different type of names. You can split them up in different percentages. So they have at least 10 different names. But plagioclase we call is a very family name for those sodium and calcium feldspars. And they are mostly common in mafic rocks, black ones. And this one, I have a rock here which contains almost only of feldspars, monomineralic rock. We call it a Labrador. Because it was found at the first time at the Labrador area in Canada. Is it Canada or is it United States? Labrador.
Canada. That's Canada.
It's Canada. Yeah, it must be up there. And also now we have found it in Norway, but it is not. It's not Labrador up in Norway, but we can find it in different type of places. It's a very, very special type of rock, and I can send this one around because if you are looking at this one and you can see the light coming in, it will be a metallic bluish color. It's very and in Norway they call it blue pearl. When they sell this stone, they polish it and sell it as gravestones, you know, graveyards, and also like walls and buildings, famous buildings for banks and insurance companies, which are very rich companies, and they also buy these ones, and it's very, very nice color. So blue pearl, they call it in Norway when it's said. So we can send it around because it's something to do with your hands when I'm talking. Quartz is also a mineral which can appear in a lot of different types and different colors. We have, it's a bad, I'm not a good photographer, but it's a bit, you cannot quite see it's so good. But I have them here. It's the same stones as I have been making some photographs of in here. So we have this quartz, and different types of quartz. You can see them down here, see them? And we have this biotite. It's this mica, black mica. And we also have this white mica. It's muscovite, as you can see. I think that they have been using this as a filler material in different industrial processes. Not the black mica, but the white mica. And also I think when in the start of the development of radio system, when they had some diodes and transistors. You know, when you were looking back on the back side in this radio monitor, there was a lot of different electronic equipment down there. And then they used at least micas. I know that they have been as a transistor. It's the same word, yes, yeah. System. So all these minerals have a technical application. Most of them, at least, have a technical application. So that's why people have been interested in them. They've excavated them and trying to find something to make money of all these minerals. We have another rock-forming minerals. This is for the black stones, what we call them. This should also be a straight line, but it's not. It's magnesium, calcium, and iron, and we call this one pyroxene, and this one we call amphibole. And they together they create 13% of the volume in the crust, and they're just black stones. Just black stones. It's very difficult when you go out with your eyes and looking at these black stones in the field to see them. But the pyroxene is more compact than the amphibole. Amphibole is elongated more than this pyroxene, but they are both black ones. And also, amphibole is more in metamorphic rocks, because this one contains hydroxide. It doesn't appear in this one. It's quite here. It's no. But these are very important, because if we have a lot of minerals like this, they can collect the heat more than in these acidic rocks. So basic these mafic rocks, they are more say heat bevara. Vad heter bevara? Beware. Bevara. Värmebevarande mineral. Yes, heat conductor. Yes, heat conducting mineral. That's right. Yes, sorry about it. So these are very important, and so this can transfer heat over for long distances in these rocks. So that is something to think about when we are looking at these protection borders when we are having this waste material down in our rocks. So, and this is also why we are using these minerals in the saunas, even like the talc basidium. So rock-forming minerals. This is pyroxene and amphibole and olivine. This is magnesium yarn silicates, like pyroxenes and amphibole. So it is. If I can try, I will just write one line here. This is decreasing temperature. Decreasing temperature. So here we have about 1200 degrees Celsius up here, and here we have about 800 degrees Celsius down here. And when this is the magma, or magma, that is the melted rocks. Before it has became a rock. This is the melted rock. And the first thing that will be crystallized is olivine. this is the magnesium and iron silica, olivine. And if we go down here, we have pyroxene. And if we go down here, we have amphibole. And even more, because now here we have 4% of water. But then we are taking away magnesium, iron, silica, alumina, and this is more and more water coming here. So down here we have 14% of water. Here is only 4%. So as the temperature decreases, we have an increase of water content in the magma. This is why the pressure also increases in this magma as it comes up to the surface area. And then when it comes to the surface, it will explode, because then there we have no protection anymore. That's why we can have these violent volcanoes exploding, like we had in the western USA, 1980. Mount St. Helens exploded. It was 3 cubic meter of rock. 3 cubic meter of rock just blowed up, turning into dust in 1 second, like this. It's great. It's good for a geologist, but not for everyone else. So when we have this olivine, pyroxene, amphibole, biotite going down like this, and when we come here, there is another line also over here, like this. It is the same temperature, and temperature decreasing here. And here we have this calcium plagioclase, calcium feldspar. Calcium feldspar. And then we go down here, sodium feldspar. And we go here down, we have potassium feldspar. And if we go down here to the potassium feldspar, we have this mica. And at this moment, down here, somewhere here, we will have quartz. Quartz down here. So this is a reaction series. When we are cooling down this magma chamber, we will have olivine together with calcium feldspar, pyroxene together with calcium feldspar, and this will create one type of bedrock. This is what we call a basalt, this lava where we have here. So this is the mafic rocks. And then we have these ones in between here. There we have the intermediate rocks. This is diorite, granodiorite, and so on. So they have the intermediate intermediate rocks, and then we have this acidic rock down here. Like granite and so on. So this is what we are thinking of when we working as a geologist, when we see different types of minerals, we can understand that it must be created at a temperature like this, and we know that it was perhaps, now I have only temperature here and this side, but we have also the pressure and different, but we can imagine. I cannot write everything. I hope you can understand that this is the minerals creating like this. They are formed down 25, 30 kilometers down in the earth crust, where the temperature is about 1,000 or 1,200 degrees, and then when it moves upwards, the temperature is going down and also building up the pressure because of the water content. There's not more water, but the percentage of water is rising, and then we will have these explosive volcanoes of this one. So if this magma is coming out on the surface, it is smooth and nice. It just comes out to the surface. And there's no explosive areas. But if we have this one, this is where you have the explosive. These magmas, they come at the ocean bottoms. This is basaltic, mafic ones. This is on the continents. We have these explosive volcanoes. This is a pyroxene, a black one, coming there. And we have this amphibole, and the most common amphibole is hornblende, and the most common pyroxene is augite. So and there's many names of different types of these minerals. You see, they can have this composition, they can have any composition here. And those geologists who have found in the microscope that this is a new mineral, he will name this mineral, and he is called Johansson, then he will be Johanssonite. And if he is called Claesson, like me, I haven't found it, it could be Claessonite, and everything. So hundreds of names inside here. But in the middle here we have one big area which is called augite. And there we have one big area for this pyroxene, amphibole we call hornblende. On olivine we have only two pieces of them, phosphorite and firelite. And this is magnesium and iron contents of these minerals. And they are the first one. Magnesium olivine is the first one ever to crystallize. So we will see if there are some